All right, welcome back everyone to the Cyberbot Educator Workshop Day 2. This is the Wednesday, March 27th, 2024 installment. As with previous, here is a link to the slideshow. And I need to find the chat. And there we go. And a reminder that you can, if you have a single monitor, you can click View up in the upper right, select Exit Full Screen, and then set your Zoom window so that you can put stuff side by side with it. And if you have two monitors, of course, just set everything up so that you so that it's arranged comfortably for you to see and work at the same time. Okay, so today we're going to work on Python scripts for navigation. I'll talk a little bit about the circuit and sound lessons, but we won't do much with those because we'll have our hands full with navigation and navigation with touch sensors, as in building, testing, and then setting up an application script with test sensors. So first up, what we're going to need to do is test the servos again, because we want to make sure that, especially that first, that everybody's servos are running, because it's easy to make a mistake when you reconnect them. And then secondly, it's also easy to end up swapping the two wires from the way they really should be. And then your left and right servos would be swapped, and the net effect is you end up going backward when you want the Cyberbot to go forward. So we'll look at that too. So first off, a review of the bot.servoSpeed method. So this statement, if you're using 18, that's going to go to the left servo. If 19 is here, it goes to the right servo. Now your velocity can be anywhere between, say, 15 and 115, and if it's positive, it makes the wheel turn counterclockwise. If it's negative, it makes the wheel turn clockwise. So what we want to do is, first off, we want to verify that a signal that goes to the left wheel will really control the left wheel, and a signal that goes to the right wheel will control the right wheel. And before we get started on that, though, I want to make sure that everybody has their editor running and the template file open. So python.microbit.org/v/3, and I'll paste that to you. Here we go. Didn't seem like that went through there. There it is. All right, so you'll want to have that, and go ahead.
Sorry.
Oh, that's okay. And then secondly, you'll want to go to your downloads and open up the Cyberbot with Blink, Cyberbot template with Blink. And to do that, you'll want to hit open. And then find in your downloads, again, it's best if you sort by date and then have it be descending. That way you get your newest downloads up top. And here I see my Cyberbot template. I'll go ahead and paste the name so you know what you're looking for, in case there's any doubt. Let's see. I'm joining from the car. I'll need to catch up when I get home, and that's fine. I just got a message from somebody who's watching or listening, hopefully not watching, in the car. And yeah, just to reiterate, we will post a recorded version of this within a few hours after the end of the session. All right, so again, you want to find, here, I'm going to backtrack. In the lower right of the Python editor, click Open. Find your Cyberbot template with blink.hex and open that. And then actually, let's first make sure that everything's ready to go. So we'll want to have the batteries in the Cyberbot. And then we'll want to make sure, of course, that we've got the USB cable plugged in to the Cyberbot or to the microbit and the other end to the computer. We'll want to make sure that the battery pack's barrel plug is plugged into the Cyberbot board's barrel jack. And then we'll want to turn on power and make sure that the two lights come on. Now, if you notice a red blinking light, like I've got right here, what that's telling you is that something's wrong with your it's mainly a low battery indicator. And so, gee, maybe, look at that. I put in a battery backwards here. So they should be going opposite directions. And the flat end should be up against the spring all the time. But on this one, the end with the bump on it is up against the spring. See that? And so now if I turn that around, my low battery light is no longer blinking. Okay, and let's see here. So, so the next thing we want to do is set the robot either upside down or on its side, like it, so that it looks like it's shown in this image right here. And so I have it upside down. So you want to have it like you want to have it like this. And as you can see, I'm not quite finished, real close, but I didn't quite make it to completely built before I had to start the workshop today. Sorry about that, everyone. All right, there's the tail ball at least. And then also we'll need to, so I'm going to be very uncareful with this. I'm just going to randomly plug the servo ports in because the purpose of the activity we're doing is to test and convince ourselves that we have the servos connected properly. So you want to be looking at your Cyberbot like that. And again, let's see here. So here is the front. This is the back, left and right. So now that we've got our Cyberbot oriented, what we want to do is run a script that, well, I'm sorry. First, we want to run a script just to make sure all the system is running properly. And so for that, we'll just rerun this template script and make sure that the P21 light blinks. Send to microbit. Kind of helps. So notice that I don't have any microbit in the list. The reason for that is because I forgot to plug the other end into my USB port. So there we go. All right, so, and then it appeared. So we'll hit connect and it's flashing and we want to see that P21 light blinking. Okay, so this tells us, you know, the absence of the flashing red light in this corner and the presence of a flashing yellow light down below means that the whole system is still fine, running, ready to go. Batteries are connected, 3-position switch is in either 1 or 2. We've got our USB cable connected and it's loading the script. So everything's green and go. See, I've not been added to the email list. Well, that's I'm sorry about that. I'll have to check for you after class.
Yeah, I can see him in line 51.
Oh, okay. I will I will check that and make sure he's in the list. I don't know how he would get left out. Okay. So here, then we want to make sure, just a reminder, and this is mainly the kind of thing you'd want to remind students of counterclockwise and clockwise, because in this age of digital clocks, for example, I heard on the radio that UK public schools got rid of clocks with hands and they only have digital clocks now because too many students didn't know about how to read a analog clock. Surprising. I don't know if it's actually true, but in a way it's not surprising because of our digital devices. All right, so what we want to do is test our Cyberbot. I'm waiting for the, that didn't work the way I wanted it to. All right, I'll just type this in. Okay, so the left wheel is going to be connected to P18. So I would like to see that turn. So let's do bot of 18 dot servo underscore speed of 65. And I'll rename this test left wheel. Okay, so remember, this has to be begotten from the template so that it has the cyberbot.py, and you can check for that in projects. And again, anytime you do a save as, or save a copy of your work, regardless of the name, the cyberbot module will come with it if it's in the project that you started. Okay, so whoopsie, got to get back to main. There we go. All right. And I'll make this turn a little bit more slowly. Let's just say 35. So, and again, here I'll show you what we're looking for. Essentially, this should be the left wheel, and the left wheel is going to be this one. And so if I run this now, the right wheel is turning. So basically, I had a 50-50 chance and I got it wrong. So I'm going to need to pull out my servo cables and swap them and plug them back in. And then the left wheel will turn. So to do that, you can simply turn off power. And then disconnect the servos. Swap the plugs. And then plug them back in. Being careful to keep the white wires toward the edge of the board and to get all three sockets all the way down over all three pins in each servo board. So I'll go ahead and pasty this, and you can try that for yourself and make sure you've got the right wheel turn, or the left wheel turning, the correct wheel turning. Got 1, 2. Having trouble following all the thumbs up. 3. Okay, I saw in the build instructions that there was a different position for the jumper based on if you were using a typical 1.5 volt batteries or rechargeable batteries. Yes, that is correct. Let's see here. Is that important to change over? All right, let me back up to the, let's see. First of all, I need to remember to go back to 116. And then, yeah, rechargeable batteries have less voltage. The servos you're using, those servos with the part number ending in 08 that you have, are designed to they're designed to be to receive up to 6 volts. Well, if you have 5 1.5 volt alkaline batteries, that adds up to 7.5. If you have 5 1.2 volt nickel metal hydride batteries, that adds up to 6. And so with the nickel metal hydride, this is actually slightly misleading. You could choose either jumper position. We just figured people would like to have it go a little faster, and it will go just a tad faster if they put the jumper on V in. If you have alkaline batteries, you want to leave it the way it came in the package, which is this jumper is over the lower pin and the center pin, and that gives 5 volts to the servo's red wire. And then this is over the upper pin and the servo pin, and this gives V in, being the battery voltage, to the servo's red wire. Was that a good enough answer to the question? And I'm seeing a fair number of thumbs up. So everybody's got their servos plugged into the correct port now. So now we want to make sure that both servos turn. Okay, before I do this, I think I'll save that. And I'll put it back in.
Andy, I have a question.
Go ahead.
Andy, how do I know it's the right wheel or the left wheel? If you can show the...
Check this diagram. So you want to set it on its nose, and then look at it and make sure that the left wheel, the one on this side, is turning.
Yeah, this is turning. Thank you.
Okay, very good, very good. And so now we want to make sure that both servos will turn. And I'll make this go for 6 seconds. And then we'll make these guys none. All right, let's test on my end, make sure that's working. Oh, I didn't set the power switch to 2. Okay, there we go. And if you go ahead and set it on its wheels after adding that, and I'll paste it through in a minute, you can always restart the script by pressing and releasing the reset button. It's right here. Right here next to the USB port. Let's see if I can get that visible. There's a small button next to the USB port, and if you press and release that, it'll restart the script. You could also just re-download the script, but if I press and release that button, it'll roll forward. Now, even though the numbers are the same, it's not rolling perfectly forward, and we'll address that momentarily. And I want to emphasize here that forward is that way. The breadboard is in the front. This little ball back here is called the tail wheel. Copy. Paste. All right, so there's your test script. Is there a benefit of using servo underscore speed of none rather than servo underscore speed of 0? The reason we use none is because over time, the servos might fall slightly out of calibration. And so instead of staying perfectly still with 0, one or both of the wheels might slowly creep along. And so by setting it to none, it definitely will stop the servo, because it actually stops sending the signal that makes the servo turn. If we make it 0, it continues to send that signal. Now, hopefully, if I did a proper job of calibrating my servos, it should still stay still. Oh, okay. It'll stay still after going forward for 6 seconds. Okay, so mine's staying nice and still. But if it wasn't, the none would take care of that. The drawback of none is that when you want the robot to come to a stop, it's just a little slower at coming to a stop. 0 kind of forces it to a stop. It gives up all control of the servo, and so there's still a little bit of momentum. It might go a centimeter or 2 further with none instead of 0. Okay, everybody. So did you get yours to most likely curve forward? Got some thumb 1, 2, 3, 4, 5, 6, 7, 8. Okay, I still see a couple people working 9, 10. Oh wow, look at all those in the chat. Okay. Well, fantastic. Just give me a shout out if you need a little bit more time, or if you have a question, of course. All right, so students can set up their script and actually run some tests and say, okay, let's put a little marker on the wheel and count how many times it turns as we run the script, and figure out how many RPMs the servos turn at these various speed settings. And then I think I talked about this one yesterday, that the speed setting, if you could actually take a whole lot more measurements, and then you'd have a transfer function curve like this one, where it stays still for a certain amount in the middle, kind of plus or minus 9 ideally. But sometimes, since the screwdriver might be a little off, it might be plus 12 and then minus 6 or something like that. So that's part of what makes it curve. And then there's just also some intrinsic properties of the servos. They're not naturally identical. And so what we need to do is set it up so that we know our magic numbers to make the servo go forward at a particular speed. And so in this example, on the first try, we did 65 and negative 65. And let's say that it curved to the right. Well, if it curved to the right, that means this left wheel is going faster than the right wheel. Right wheel's slower. But it's always better to slow the faster wheel, because once you get to top speed, you can't speed up the faster or the slower. You can't speed up the slower wheel necessarily. You have to slow down the faster wheel. So I always have it so that the students slow down the faster wheel. Okay, so let's say that we drop it by 10. And so our second try uses 55 to slow down that left wheel. And then it turns the other direction. And so, and maybe it even seemed to curve about the same amount. So then the students go, aha, well, let's try 60 instead. And sure enough, that gives at least close enough to straight ahead. And so that is what I would like you all to do. And let's do it with the number 75. So I'm going to give you a slightly modified script here. And we'll have you all right. And so we'll have you try this out and find the magic numbers to straighten out your servos. There we go. question. So if it went straight first try, you don't want us to change anything. Well, you know, it would be worth just making it curve to see the effect. But yeah, if it went perfectly straight, then yeah, there's certainly no need to change anything. So I'd like you to remember that the left wheel here is bot of 18 and the right wheel is bot of 19. And then for forward speed, I neglected to mention, you're going to have positive values on the left side and negative values on the right side. And the reason for that is because to move forward, if you're moving forward going this direction, looking at the left side of the bot, the wheel has to be turning counterclockwise. But if you look at the right side of the bot and you know that now forward is this direction, notice that the wheel has to be turning clockwise. And so that's why we have opposite values here for forward on the left servo and the right servo. And so keep in mind, once again, that your left servo is connected to P18 and your right servo is connected to P19. And then you'll be adjusting your values to try to get a straight ahead path while testing over 3 seconds. And
We
I'll
have
go
a
ahead.
couple of questions. One is regarding your graphics, if they are available in Learn.
These graphics will become available in Learn. Some of them, like many of the graphics are available in Learn, like this one. Okay, so we'll look at, we'll go ahead and look at the, this, so for example, this picture right here is this one. But this graphic is new. This graphic is new. Likewise with this one. And so these are all in the queue for updates on Learn, but they're not there yet. But I figured since you're making the effort to come to the course, you might like to have some added bonus. And so here you go. And then you know, hopefully by this coming fall, we'll have it all set up so that these nice new images are also there. Many of them are, as I mentioned, like this one. But yeah, these guys right here are not up yet.
And we also have a report of an error message saying failed to build hex 5.
Failed to, wow, that's pretty interesting. Take a look at your project settings. Make sure cyberbot.py is in there. And make sure cyberbot.zip is not in there. Also, if you could give me the exact message in case there's more to it. Let me see if I can find. Slide 121 was the one you were curious about. Yeah, so that's one that was in our other textbooks, but didn't make it into the web book. So I redid it most recently. But you're welcome to take it straight from here. Just take a screen capture and put it up for the students. And but yes, we're trying to get those. These are all in the queue for updates. Okay, and then let's see. So even if both servos are calibrated correctly, they can still rotate at slightly different velocities. The answer is yes. They're not precision devices, and so they each one has a slightly different. It can be slightly different clockwise and counterclockwise, and it can also be slightly different just in terms of the internal resistance of the gears and you know, the motor's behavior. That all varies, and so we're going to calibrate in the software. So if it went straight first, we saw that one. All right. Without changing the servo speeds, is there a way to make the bot go straight? Only if you are using servos with feedback. So there are fancier servos. We try to keep the price of our stock kit reasonable. There is an upgrade kit that has what are called they're branded Feedback 360 servos. And here is an example of how they work. And the Cyberbot board has enough smarts to essentially keep the wheel moving at the requested speed, but it can also maintain even requested distances. So keep your eye on this little white mark right here. It's set up so that the wheels only do full turns. And so it should come to a stop. There's that reset button I mentioned earlier to restart the script. See how it stops at the same spot? So that kind of motor is a little more expensive, but it is a way to avoid the software calibration that we're doing on our robot with the script. Frankly, I think it's nice for students to do that software calibration, and then like some teachers decide to get these and have the students swap them out in a second semester or a second year. Ari, are there any other questions I should jump on?
We are working the other one with the hex file problem, but seems to be the library. So we are troubleshooting in the chat.
Okay,
She
okay.
said that it says that bot is not defined. She gets the error message, which usually is the lack of library.
Yes, it is. In other words, what it would look like is cyberbot dot, if you go to, so it normally looks like this on the left panel, but if you click project down below, cyberbot.py would be missing. And so it would look like this. And notice, see the red dots that appear? It no longer understands the bot calls, no longer understands servo speed. It doesn't understand bot, so it doesn't even look for servo speed. And so there's an open file in the project panel here, and you can hit open. And assuming that you've downloaded the Cyberbot microbit stuff and unzipped it, you can go spelunking down in that folder, find cyberbot.py, double click it, confirm you want to add the module, and then you're back in business. And the details of all that can be found. Sorry, my office partner has an incoming phone call, but she's not in the office today, so it's going to ring for several times. Okay. So add modules to your microbit is the tutorial. And normally what we do is we say, hey, just download this and start with it. And when you download it, you have to make sure to right click and select Save Link As. But we also have all that other stuff I just showed you. And there's a video all about it. And then there's step-by-step instructions for downloading and unzipping the zip and adding the file to your project. So all of that stuff is essentially down below, and it just depends on what level of depth you want to take your students through. If you want them to see that you can add a module to your project and that it extends its abilities, that's one way of doing it. But if you just want them to be up and running quickly with a minimal headache level, then just have them download the template and remind them to open it every time. Okay, so how are we doing on the straight ahead part? Are our robots going reasonably? Okay, yeah, I see. Okay, Stephen. Thanks for the overall number of thumbs up. It does take some trial and error, and that's a real technique. So I do recommend it. Now, turning. If we look at this, we've got our, right here, we have our left wheel turning forward and our right wheel turning backward. So if we wanted to make our Cyberbot rotate right in place, what values would you choose? What value would you choose for the P18 side? $65. Okay, yeah, that's a reasonable one. Okay, and then what value? And yeah, there's some good answers coming through on the chat. All right, then if we put 65 here, what value would we choose right here? The same value, yes. So we'd want to have 65. That makes this wheel go forward. So that goes right here. And then 65 right here, that makes this wheel go backward. And that's how we do a right turn. And if we want to do a left turn, well, not too hard, just make both values negative. That backs this wheel up and makes that wheel go forward. And so here is the example with 75. And here is a test script that I would like you to try, and hopefully I managed to succeed. Yeah, there it is in the teacher or in the slide notes, like I intended it to be. So again, you will need to paste this into a project that has that Cyberbot module. And if you opened Cyberbot template with Blink, you're ready to go. Oops. And what this one is going to do is it's going to go forward full speed, might curve a little bit since we didn't have it. For each speed, you're going to have to probably test. It's not like a constant offset. It probably increases linearly with speed, though I can't actually no, I doubt it's even linear. So you'll want to, you know, if students have a set of favorite speeds they're going to use, you know, pick your offset to slow down a wheel at a given speed. Don't do that though. We'll just let it curve a little bit and that's fine. We just want to verify that it goes forward, turns left in place, turns right in place, and then backs up. And let's see, did I give this to you already? Yes. Did you say 18 was left and 19 was right? Yes, I did. Yeah, P18 should go to the left servo and P19 should go to the right servo. So this servo should be connected to P18. This servo should be connected to P19. And forward is this direction. Forward, backward, left, right. And that is all from this set of this chapter. Now I'm going to paste one for you that makes it go forward and then to the right. So after you've tried the forward, left, right, backward, and made sure that it works, try your forward and turn right and stop. And for that, if you wanted to tune the right, which let's leave that for our spare time because there's lots more to cover. Although, you know, if you want to try, like if it didn't turn right, if it didn't turn far enough right, you could increase the 600 to 700 or 800. If it turned too far right, you could reduce that 600 to 500 or 400 or whatever. And then, of course, zoom in on whatever gives you a perfect 90-degree turn. So instead of adjusting the speeds here, which you could also do, the best first cut, though, is just to adjust the amount of time it executes the turning maneuver. And then that also applies to distance. Like if you want it to go the same speed, but a different distance, like let's say you want it to go twice as far. Well, instead of 3,000, you'd make it 6,000. If you want it to go half as far, maybe 1,500. And again, that's the sleep value between one maneuver and the next that controls how far it goes. Does anyone have the transcript from the last video? I watched it, but forgot to download the transcript. Yeah, I can, if you email me, I can go ahead and send you the transcript. Because I did take the video down just before the class started. Okay, so how are we doing? Does everybody have straight ahead and right turn? Okay, fair number of thumbs. All right, and okay, so just give me a shout out if you're still working on it. And again, you don't really have to tune it. You know, if you want to try changing the number ones just to see the angle differ slightly, that's fine. But what I want to show you is a trick because if you tell students, okay, well now you have one part of a square. Some students' first inclination is going to be to copy and paste it 3 more times to have their square. And since we want to impart some valuable computer science lessons, the next step would be to say, to go back to our repeat things from the homework before the class started and do something like 4n equals 0 to 4, colon, and then indent everything else. And watch this trick for indenting everything else. So I'm going to basically shade what I want to indent, which is lines 5 through 11. And then I'm hitting the tab button. And see how all of it jumped in? And I used the wrong, for some reason I lapsed into our PBasic programming language. Okay, for n in range 0, 4. There, that's much better. So I'll go ahead and paste this one to you. Forward, right, stop, X4. Well, whatever. Save. Oh, geez. Control A, Control C, select chat, Control V. Okay, so so there it is for you. And after calibrating your sleep below the turn in place, students can get an actual perfect square. And all we want to do right now is just verify that it goes forward and turns right a certain number of times. Incidentally, just a side note, I had difficulty showing you the reset button on the microbit earlier. If you want to leave it connected to its USB cable and just restart a program that you've already loaded into the microbit, you can press and release this little button underneath the microbit. Now, when you have the USB cable unplugged, you can also just turn power off and back on, and that'll restart the script that's loaded into it most recently from the beginning. How do you set the indent for a whole group again? Very good question. Basically, all you have to do is shade it. So, and you can do that by clicking and dragging, or you can do that by placing your cursor and holding the shift key and doing the down arrow. But regardless, once you've got it shaded, if I want to outdent, it's shift tab. And then if I want to indent, it's tab. See here. Oh, I see. There we go. Somebody that was also answered in the chat. Thank you. So were we all able to verify that if we tuned our turns that our robot would do a square? Did it go forward and hang a right turn 5 times? Got 1 thumbs up. Couple more. Am I to take it that y'all are still working on this then? Oh, here's some more thumbs up. Since the microbit uses MicroPython and instead of regular Python, would it be a bad idea to direct students to the general Python documentation? Or is it mostly the same except for specific libraries? I think that if you set up your class so that they do a set of regular Python tutorials, most of the beginner stuff, loops, conditionals, so the if statements, the for statements, the while statements, that all is common to full Python and MicroPython. The place where it ends up not working so well, I mean, there's a few little things in the basics, but generally it's trying to import a library. Like if you import some kind of encryption library in your official Windows or full computer Python code, it's a huge library. There's no way it's going to fit in the microbit. And then there are a few commands here and there that are off, but it's generally any normal computer Python tutorial, if it's just hitting the basics like counting and etc. That's an okay tutorial as well. And students can usually pick up, hey, this is MicroPython. It has some limitations. You're not going to damage their brains in any way, shape, or form by having them, need to adapt to a slightly modified version of the language. That's a good experience, I think. Should we have the rubber ring on the wheel? Yes, absolutely. I have to jump off Zoom. Okay, well, that's fine. Just make sure to catch us on the recorded version. See here. How run programs without the USB cable connected? Okay, well, just unplug the USB cable. So for example, I'm going to load this script into my Cyberbot, send to microbit. Okay, and it's going to start going. And what I can do at that point is turn off the power, unplug the cable. Now with the cable unplugged, I don't even need to go under there and hit the little reset button. All I need to do is turn it back on, and then the script will resume. Or not resume, it'll start over from the beginning. Okay, also you can connect via Bluetooth from a smartphone. Now that is true, but the Bluetooth, the Bluetooth takes up a tremendous amount of memory, and so you end up not having much left for your script, number one. And number two, yeah, I have not seen a lot of success. Anybody who uses a tablet to program their microbit uses an OTG connector if they're doing it with the Cyberbot. A third thing is that if you have any use of terminal, I don't think it has the terminal feature. I might be mistaken about that. I want that hello to appear. Press and release the reset, see if it comes up. This is that thing I mentioned that you have to, oh, it's because I didn't have power on. Okay. Send to microbit. I don't know why that's not printing. Well, at any rate, another thing you're missing is the terminal when you're using the smartphone slash. Okay. How can I use these cyberbots for students to imitate Red Hat teams and Blue Hat teams? Can I ask you to wait till Friday for that one, Melissa? There's a full cybersecurity. I'm going to talk about the cybersecurity chapters on Friday.
Sounds great.
Okay, excellent. I guess I can give you a short answer though, and that is that essentially, oh, I ended up in cybersecurity by accident. That's more microbit centric. Cyberbot is a superset, and just wanted to, hey, why am I not in? Okay, so we have here basically two chapters on radio communication and then some radio control stuff. And we're not using the addressing system in the microbit per se. And so it is like the internet, students can just kind of see the communication of other students going on. And so then we go through encryption and some different attacks and defenses that can be done with the microbit. And then there can be Red Hat, Blue Hat competitions with the Cyberbot. All right, so it is 2 minutes past the hour. Let's reconvene at 7 minutes past the hour. All right, welcome back, everyone. So there are many classroom hours of material. I can't cover it all in 6 hours. So what I'm going to do is just whiz through a whole bunch of stuff, and then we'll slow back down when we get to whiskers. So I just want to point out that we did turning in place, but you can also cause one wheel to stay still. If the other turns, you'll get a pivot turn where it pivots on one wheel. Additionally, if you have one wheel going slowly and the other wheel going much faster, you have kind of a tight curve. If the wheels are actually kind of going more the same speed compared to this one, then you have a wider curve. And there's fun stuff that students can do, like this would require a for loop for one of the wheel speeds in order to get a spiral. This would be an arc turn, or approximated by an arc turn, a straight line, another arc turn, and another straight line. To see a practical application, you can set a water bottle somewhere and have them, and then put down some tape around the water bottle and have the students try to go 1 meter, circumnavigate the water bottle, and come back. We end up talking about functions, which are predefined pieces of code. So here's a function, and then here is a function call that makes the script jump up to the function definition, and then do the speed and the amount of runtime. And then when it runs out of statements, it comes back to the next line, which happens to be another function call. Function calls can even be really slick. Like here's one that accepts parameters. So the function definition wants the left and right velocity and the runtime. And it's even set up so that it corrects that, or it makes it so that you can say, oh, my forwards are all positive. So I'm going full speed forward here, positive 115, positive 115. And then the function itself makes the right wheel speed negative for you. Makes it really easy to set up a nice sequence of statements to navigate like a maze or something like that. We also go into circuits, and I do need to talk a little bit about that, just a little bit. You know, given another couple hours, we'd probably build a warm-up circuit first, but we will instead have you build your first application circuit for the robot, as opposed to doing a few circuits for circuit's own sake. The thing to know about this white breadboard is that it's organized in groups of 5 sockets, and there's 2 columns of groups of 5 sockets. And if you want to connect 2 wires together, you just need to make sure that it's in the same group of 5 sockets. So here's 2 wires connected. Here's 2 other wires connected. Now you can put a jumper wire to connect 2 groups of 5 sockets, and then you have even more sockets for connecting wires or part leads together. So these are all examples of how to connect wires together. These are examples of wires that are not connected together. So see how it's in one row of 5 here. Well, this is a completely separate row of 5, so they're not connected. This is a row of 5, which is separated by a valley from the other row of 5. Remember, there's 2 columns of rows of 5, so these are not connected either. That's why you'd have to use the jumper wire to connect them, and then you can actually connect the 2 wires together. So that's how connecting wires works on a breadboard. The breadboard also has power up top, so these are black sockets. It has I/O sockets along the side. These are going to be ones where you tell your script to either control the pin, like turning on a light, or control the socket, for example, making it turn on a light, or monitor the socket, as in, is a whisker pressed or not, is a button pressed or not. This is ground, that's the negative terminal of the battery pack. And then 3 and 5 volts are just kind of intermediate voltages that are lower than the actual battery voltage. And they're available to power certain devices on this breadboard here. There's also 3 sockets for measuring voltage in more than just a 0-1 fashion. You can actually measure 2.2 volts or 2.7 volts. So those kind of numbers you can get out of these A to D sockets, and a little bit of math with your Python script. Likewise, D to A, you can set certain voltages. And the lessons go through, how do circuits work? How do electrons flow through a circuit? What are the schematic symbols? How does a schematic work? How do you identify resistors? These are parts that resist the flow of electricity, and they come in different values, and the values are denoted by the stripes on the resistors. And so students can start by making a simple light circuit, and then writing a script that can turn the light on. It's connected to P12, so baud of 12, write digital 1, we'll turn this light on by applying 3.3 volts to the circuit on this side. And then there's ground or 0 volts. So there's electrical pressure across the circuit. It will force current through the circuit. That will make the light turn on. Then after a half a second, baud of 12, right digital of 0, we'll put 0 volts here at P12. There's also 0 volts down here at ground. So there's no electrical pressure across the circuit. So current stops going through it and the light turns off. And we talk about how that happens inside a programmable device. There's also some lessons on sounds, and students really like to elaborate their Cyberbot with, for example, a victory song at the end. And so we have them plug a speaker in and learn how to write scripts that either make special effects or musical sounds. And we also introduce the push button circuit and talk about how to wire it up and how to make it so that the microbit monitors the button and then lights up the light when the button is pressed, things like that. And there's how it works information about that too. And with that, we will move on to touch navigation with Whiskers. Pretty cool chapter. And it uses some of the circuit building skills that students will have done. And you're if you're new to circuits, this might be a little uncomfortable, but don't worry, we'll get everybody through it. And then when you're done, here's an example of how your Cyberbot should be able to bump into an object and detect that it did so, and then pick a new direction to travel because it recognizes through the script that it bumped into an object. And I'll just give you the chapter. Copy. Paste. So that's the cover page of the chapter. And then if you go there, you'll see that it's split. So this is the chapter here. And then it's split up into activities. And the first activity is going to be to build the whisker circuit. And so what it shows is how we're going to loosen these screws that are holding the standoffs on the front of the Cyberbot. And we're going to hook the whisker around one screw below the nylon washer. You don't need to take the screws all the way out, by the way, just loosen them enough to hook the whisker in there. And then the other whisker will be hooked around the screw above the nylon washer. So make sure there's some offset, that the one is a little higher than the other. And I have some better things to show you. So first of all, what I'd like everybody to do is gather these parts. So there's going to be 2 whiskers, 2 3-pin headers, and 2 resistors with the red, brown, gold stripes. That's a small resistance of 220 ohms. And the gold means plus or minus, I think 5%. And then we'll need 2 high value resistors, 2 resistors that really prevent the passage of current. And those are going to have the brown, black, orange, gold. And again, students will have gone through an entire activity where they learn how to identify resistors. And so we skipped over that in the interest of time and having you try out some of the main robot applications in 6 hours of time. So please go ahead and chat me a thumbs up when you've got that going. Guess I'll keep everybody visible. So any thumbs up that, okay, 1, 2, 3, 4, 5, 6. Doing good, everyone. Careful to get brown, black, orange, and not brown, black, red. I'm actually not sure that that makes any real huge difference, but just in case. brown, black, red is 1/10 the value. It's 1 kilo ohm or 1,000 ohms. And so we want to do brown, black, orange. Is everybody okay? Got another thumbs up. I'm still seeing some people looking down, so I want to make sure that everybody's got their resistors and parts. Thank you for the thumbs up. And what I'll do is I'll go ahead and paste you a link to the page with the picture that we're on. Where is it? I wasn't aware that we didn't have the picture of the parts. Well, I think I'll leave this up for a little longer. Does anybody need some extra time? Give me a thumbs down in either the chat or the screen. Are we all set, or do we have anybody who's... Okay, I got it. Yeah, just a minute. Thank you.
Yeah, and you also have access to this slideshow that will be 190.
Ah, good point. And I might even be able to, I think if I paste this link in, you'll get straight to it. Okay, so that is the link to the current slide 190. Okay, very good. Well, I think we're good. Give me a shout out if we're not, and I'll go back. So again, the whiskers, you want to loosen the 2 screws, give it a few millimeters, enough to get enough to hook the whiskers around the screw, and then you'll need to put one below and one above the nylon washer that's sandwiched in there. Okay, now after that, our robot's we want our robot to look like this when we're done. And heads up everyone to the slideshow for just to the Zoom for just a minute here, and I'll show you what we're looking for. So here is the whiskers. Each whisker is in the standoff, and you've got it tightened back down. And then the whisker comes like this, goes up and then out, and then goes from here up and out. And then the 3-pin headers, those things with 3 pins, are shoved so that the black plastic in the middle of the 3-pin header meets the surface of the breadboard. You're going to be inserting those here and here. And then this row of 5 is going to have a brown, black, orange, a 10 kilo ohm resistor in its socket. And we want everything to sink in at least 1/4 of an inch. And then a red, red, brown in the socket too. Now the brown, black, red is going to go up to 3.3 volts, one of these black sockets up here. And then the red, red, brown is going to go over to the P7 socket. And again, that also is a black socket. It's a very common mistake for students to make, to put the resistor in the breadboard next to the P7 socket. No, it has to go in the black P7 socket. These aren't connected to anything. P7 is. The same applies to this upper one. It gets a 10 kilo ohm resistor that goes in the same row of 5 and up to 3.3 volts, and in the same row of 5 and over to P9. And what I'm going to do is give you a close-up. But first of all, so this is calling out which one are the brown, black, oranges, and which one are the red, red, browns. Okay, and it's a nice close-up. But one other thing I want to point out is that you need to make sure when you tighten your whiskers that they're, and you might want to loosen them and retighten them a couple times until you've established an air gap. And that air gap should be about 1/10 of an inch. So these little sockets are 1/10 of an inch apart. So you want at least another 1/10 of an inch, 1/10 to 2/10 of an inch in between the 3-pin header, the pin that's closest to the whisker, and the whisker itself. And the reason for that is because the whisker should be not touching the 3-pin header when it has not bumped into anything. When it bumps into something, the whisker will get pressed into the 3-pin header. It changes this whole circuit. The script will recognize that through monitoring the circuit, and then it'll be able to decide to back up and go a new direction. And so I'll leave this up here. Or no, should I leave this? I think I'll leave. So remember the air gap. And then hopefully this one is going to be the best one for building from. And I'm also going to see if I can find a page for that. Hey, Ari, my view of the attendees mysteriously disappeared. I'm wondering if you know of any way to make that come back through the little control bar. I've been looking, but I can't seem to find it.
I see. If I click in the view in the upper right, I'm not in full screen mode. And if I click in view in the upper right, I can change to standard, side by side, gallery.
Yeah, problem is I don't even see view. The entire window just disappeared. And I've tried pointing at zoom, and I don't even see it there. See if maybe it's on another screen. Nope. Does it matter which whisker is above and below the washer? Not to my knowledge. I do not think so. Well, folks, it looks like I might not do such a great job of counting thumbs up anymore unless you chat them to me. Sorry about that.
So it was the participants list that you were using?
Well, I used both the chat and the little thumbnail view. I guess oh, you know what? I have a second computer. And so I'm just gonna cover up that computer with the thumbnail view. All right, so I can see everybody. If you see me turning my head to the left a lot, I'm just checking everybody to see how they're doing. Okay, so we're good. Now, how are you guys doing with your whisker construction? Got one thumb up, and then 1, 2, 3, 4. How do I connect the whisker? Okay, connecting the whisker is, are you talking about putting it, hooking it around the screw and then tightening it, Lexi? Oh, okay, Lexi sees it now, good. And remember, when you tighten that whisker, you're going to want to have an air gap between the 3-pin headers. So what's going to happen here is that, let's see. So what you can do is, if you press the right whisker, it's actually going to touch the left 3-pin header, but that's okay because our script will figure all that out. But if it touches the left 3-pin header, what's going to happen is that a light on the right side of the microbit will turn on. So if you press this whisker, this light should turn on. Likewise, if you press the other whisker, the other light should turn on. And sure enough, if you press them both lights should come on. And then if you release them both, no lights should be on. So when you run the script and you're not pressing the whiskers, it'll start with no lights, so it won't seem like anything's happening. But then if you press one whisker against its 3-pin header, the light will come on, or the other light, and if you press them both lights should come on. And this is a crucial test, and a lot of you are going to find that you made a mistake building your circuit. So we'll need to go back and look real closely, make sure that everything's plugged into the right place. Let's see, could you go back to that picture again, or perhaps add a link that gives directs to connecting the whisker? Okay, so Lexi, I think you're asking about this slide, and I'll go ahead and paste you in a link. Okay, that should take you straight to the right slide. And then also, I'll give you a link to the student tutorial page. That might even be easier to get to.
Can I get that also?
Oh, I think I pasted it to everyone.
Okay.
So it should be in the chat. All right, so we need to get you guys a test script. So I'd like you to make sure that a light comes on the microbit display that indicates which whisker you are pressing. It's on its way to the chat. There you go. All right. Let's see if I can do my whiskers in record time. And then when I come back, we'll be able to verify that everybody else has their whiskers going too. All right, so I'm hooking the whisker around above this washer. Tightening it down so that it's kind of parallel to the front of the breadboard. And here's the second whisker, and interestingly, both my lights are on, and that's because of the way the microbit behaves when a circuit is not connected to it, since I don't have my circuit built yet. So basically I want you to press one whisker and make sure that its light comes up, and then press the other whisker and make sure that its light comes up. And then when neither of them are pressed, you don't want to have any lights on. And when both of them are pressed, you do want to have lights on. Yeah, and be careful also, because you want to have red, red, brown, not red, red, red for your resistors that are connecting to the I/O pins. Incidentally, I mentioned having a magnifier and using that for your circuit. And my cell phone is my magnifier of choice. And so basically, when using a cell phone, there's often a magnifier app, like mine is right up top here. And so you can change the level of magnification here. And for selecting resistors, it's nice to be able to zoom in, and you can very clearly see the color codes usually on your cell phone using the nice magnifier feature. And so here are here are my red, red, brown resistors. This can also help to troubleshoot the circuits. And so again, once you've got it all connected, and incidentally, I should have told everybody to turn off their power before doing this. But normally nothing bad actually happens. But with the power in the 1 position, I have no whiskers pressed, and so no lights are on. Now, if I press the left whisker, the left light turns on. And if I press the right whisker, the right light turns on. And if I press them both, they both turn on. Okay, so now let's troubleshoot anybody who still doesn't have that set of behaviors. Actually, was that visible or not? I just realized that my microbit was off the screen. So no lights on, no whiskers pressed. Right whisker pressed, right light on. Left whisker pressed, left light on. Both whiskers pressed, both lights on. Okay. Oh, sorry. So you could see it. Okay, very good. Is the chassis the ground? Is that how the circuit's working? Yes, absolutely. Somewhere way down here, I have a, so basically this is the ground and it comes along the whisker and all the way up the entire whisker. And when you are pressing it, that ground presses up against the 3-pin header, which goes to P7. So all this right here is going to be 0 volts. And when you don't have it pressed, everything is 3.3 volts. 3-pin headers, this resistor, P7, all that's 3.3 volts. Because no, when an IO pin is monitoring, it doesn't apply voltage, it just silently monitors voltage. And there's no other voltage connection. There's just the 3.3 volts here. So it's sensing 3.3 volts. Can the pins accept 5 volts as well? No. If you use a large resistor, I think 3.7 ohms is the minimum resistance value for these IO pins. As long as you use a 3.7 or larger ohm resistor, kilo ohm resistor, then it's okay to connect 5 volts to the IO pin.
And Andy, that's for the propeller chip, not for the microbit, right?
That's correct. The propeller chip is underneath the board. I did point it out on Monday. It's basically, if you look between the black Cyberbot board and the aluminum chassis, underneath the breadboard, if you look up underneath the black Cyberbot board, you will see the square propeller chip that is doing all this stuff. And then it just accepts messages from the microbit. Okay, where can I find a technical diagram or spec sheet for the Cyberbot? There is product documentation, I believe, on www.parallax.com. If we do Cyberbot board. Okay, here is the Cyberbot board. And if we view the product, go to downloads, there's a Cyberbot board product guide. And I'm pasting in the address for that. So there's the technical documentation for it. Okay, so let's have some fun with this. Incidentally, here we go. Now, I don't know that this is going to paste through. I think there may be too much code to paste through this. So let me see. I'll try it. Try pasting you the code from the roaming application, but I bet it's not going to go in. Oh, it did. All right. Well, there's roaming with whiskers for you. And so and remember I mentioned the dedicated functions that can go backwards, left, right, etc. Well, here they are. And the basically after checking the whisker states, the program has a set of if, else statements that just call the functions to maybe back up and turn right or back up and turn left, or maybe just go forward briefly and then check again. And when we run that, send to microbit. Now you'll need to put the 3-position switch in position 2 for it to start roaming. And so here we go. And as soon as I tap the whisker, it's going to back up and turn a little bit. And what we'll need to do is tune this so that it turns and backs up a better amount, because the default one kind of does the action, but it's up to the students to actually tune their turning time and their backing up distance so that it's favorable. Okay, so let's see if we can get this to be large enough to show. Okay, so here we are going forwards. And it backs up and turns a little bit. But that's not backing up enough or turning enough. So what I'm going to do is adjust the script a little bit. Like we want it to back up, I'd say a good 800, let's say 750. And then I think probably turns should be in the 500 range. I think that'll give us some better behavior. So here is the modified script that should actually make it behave more like we saw in the whiskers video. Okay, so if I load that into the microbit, and I had the 3-position switch set to 1, and then if I set it to 2, that's much better. Okay, so the second script I pasted in is probably the one you want to go with. And I'd like to see some thumbs up once you. All right, that's a good looking bot there, Murphy. Michael, good job. Jackson, excellent. Oh, hey, we got a whole bunch on the chat. Perfect. Nielka, Maria, Alvina, Jess, Caitlin, Great job, all of you. Billy, all right, way to go. Gianni, very good. And I hope I said your name right. And then did anybody thumbs up on on their camera or using the reactions buttons? I didn't see it if you did. See, almost. The CH is, oh, Kiani. Okay, thank you. Okay, if it's going in a circle, then does that mean one wheel is faster than the other? Yes, possibly. Let me think about this. It should just turn in place if it's going in a circle by turning in place, it might mean that it thinks that one whisker is constantly pressed. If it's kind of curving in a large circle, yeah, that's the thing where you'd go back into the script and you'd adjust your forward speed to slow down the faster wheel. Thanks, Kiani. And E. Murphy, good job. Great job. So, Alexia, is it making a wide arc as it roams forward, or is it just spinning in place? It's making a 1 foot radius circle. Oh, that's a big difference. Yeah, get with me after let's look at that after the recorded part, and we'll see if we can do some troubleshooting. All right, well, excellent job, everyone. Let's talk about the homework for Friday. There's 2 parts to it. One is going to be disassembling your whisker circuit after you've got it running to your satisfaction and putting a new circuit on. And we're going to have you do that. So I had you do the whisker circuit mostly from slides and scripts that I supplied. But, you know, to see what it's like for the students, we'll have you go through the student guide for the infrared detector. Now, the infrared detector is, just a second, here's the video, I believe. No, that's the whiskers. Okay, here is infrared light navigation. So it's basically, if you look at the Cyberbot here, there's 2 tubes sticking out and 2 black tubes sticking out in front of the Cyberbot. Those are like, those are infrared LEDs. They're like little infrared flashlights. So it's a light that we can't see. It's outside of the visible color spectrum. And then there's 2 little circuits on top of the breadboard that that can see reflected infrared. So if this infrared flashlight goes out, hits the box, and comes back to the receiver tells the I/O pin about it, and the microbit detects and responds accordingly. And so if we go back to the beginning of this, here comes the Cyberbot, and it got close enough to see the obstacle, and when it did, it turned and went another direction. And so what we're going to do is we're going to build that circuit, and then we'll test it and troubleshoot it, and then do a couple of fun applications with it next session. And so just a few heads up, infrared, there will be some parts. The infrared light can sometimes be seen through cell phone cameras. Some of them filter out infrared. But here's me pressing a button on an infrared TV remote, and you can't see it with this particular camera that I took the picture with. But then I shined it into my cell phone and took a picture of that, and you can see that there's a flickering light there. Well, I mean, it's not a movie, but it's a flickering light when you're looking at some cell phones, and so that's the same kind of light that the Cyberbot's going to use. It's going to shine the light outward, and then the same kind of infrared receiver that would be in an old television set that had the kind of remote that you have to point at a TV set to get it to work. There'll be a parts list in the tutorial. And so here is the tutorial. Here's where you'd be. And you'll want to be careful because there's a clear infrared LED. That's the big one. It's got the large dome. It'll have roughly the same shape as some red lights, some red LEDs that you'll find in there. And then there's a smaller clear one with a kind of a flat top and or flat-ish top. And so that one is actually a visible light sensor. So the infrared LED is the one that's larger. It's got a larger clear plastic case of the two. And it shows how to put the infrared LED into the LED standoff. That's this tube, and the LED shield, that's the little top. And they snap together so that it's completely enclosed in this little black tube. And then you'll be very carefully building the circuit. Make sure not to have power on, even unplug the LED. And you'll want to go through and really very meticulously make sure that everything's plugged in as shown. Yeah, that'll be very important to make sure that all the little wires, that each end is going to exactly the right bomb site, so to speak, the right socket. And please check it over twice, at least 3 times would even be better, just to make sure you've got all the stuff right. We'll troubleshoot, and invariably there will be a few mistakes that we'll have to correct. And we'll do that on Friday. So again, make sure you're using an infrared LED and not a photo transistor. Make sure to properly put it into the thing, the black tube, that being the LED standoff and LED shield. And then you'll be plugging them in. The black tube will plug into the top 2 sockets. These anode leads, these things that are marked anode lead, are the longer leads. So the longer lead is going to go in this upper row, shorter lead in the lower row. And then likewise, the very top row is where the longer lead is going to go in. And then the shorter lead is going to go 1 row down below it here. And then below that, there's 3 leads of the infrared receiver. And above the IR LED, there's 3 leads of the infrared receiver and your resistors and jumper wires. So be very careful as you build this. Remember that the anode lead is the longer lead. And you'll also be getting a homework. You'll also be getting, if you have not already joined the learn.parallax.com website or registered as a teacher with the learn.parallax.com website, you will receive a notice that, yeah, you've been added to our website. And then you'll get a message like this one. This is from Stephanie, but Ari, I think, will be sending out the messages. And so basically the other piece of your homework is you just want to make sure you can log in to learn.parallax.com. Either if you've never signed up before by following the instructions that Aristides sends you, or that Ari sends you. It should say Ari Alvarez, I think, in the email name. Or if you don't get this kind of email, that means you've probably already signed up with learn.parallax.com, and you'll just want to go and sign in. And by signing in, I mean go to learn.parallax.com and then click the educators link, and then follow the login link. And I'll even, okay, so for those of you who have already already signed up with learn.parallax.com, you simply, I think I replied to a particular thread. I didn't mean to do that. Here we go. Okay, there it is for everybody. So that's the sign-in link. And so that's for those of you who have already signed up with learn.parallax.com. And then again, you'll get an email if you had not previously signed up, and just follow the instructions.
Yeah, we have about 26 new accounts. The other 10, about 10 already had the account.
And I'll be emailing you a little summary of all this, along with a link to the recording of today's video, in case you want to go back and check with anything. So that pretty much wraps it up for today, except for one very important detail. Unplug power when you are done. So let's go ahead and demo that in no uncertain terms. I am unplugging the barrel jack from my Cyberbot, and I'll also go ahead and unplug the USB cable. So this is the way I prefer to store my Cyberbot robot. That guarantees that the batteries cannot be drained and you can still leave them in the holder. All right, well, for anybody who has questions or comments, please stay after the recorded segment of the workshop, but this is the end of the recorded session. I really appreciate you all, and thank you for coming today, and we'll look forward to seeing you again on Friday. Same link to join the meeting, same time, just different day. All right, so we'll see y'all on Friday, and we'll see some of you who want to talk in just a minute after the recording stops.